Okay. Please let me know if you can see already the slide on the introduction to reactor design. This is actually divided into three sections: the introduction to reactor design, the design of ideal reactors for single reaction, then it has a continuation, another set of slides still on reactor design, and a third one. Okay, but for now, we will be designing only one particular reactor for a single reaction. So we're not talking about multiple reactions here, just single reactions uh, facilitated in any of the three ideal reactors. Okay, so this is the intro to reactor design. Now, we've learned in the previous three modules that the rate equation is an intensive measure. So the rate of a particular reaction is not dependent on the amount of the system that we are measuring the rate of. So it's an intensive measure. And this rate equation also tells us how rapidly a component disappears, referring to the reactants, or how it forms in the case of the product. Okay, so its rate of formation and disappearance is a function of the conditions in that particular environment. Now, and that we know that when we speak of a rate equation, it is a differential equation. Contrary to what often others confuse it as the rate law as well. So the rate law is just simply the rate equated to the product of the rate constant times the concentration term or terms raised to the corresponding order of the reaction based on the species of that particular reaction. But when we speak of the rate equation, we change the rate expression, rate R on the left side of the equation to the derivative of the concentration with respect to time. Or it could also be derivative of conversion with respect to time. So that is why it's a differential equation. Now, what do we need to know in reactor design? So number one, we need to know the size and the type of the reactor that is best suited for the reaction that we need to carry out on it. So oftentimes when we speak of the design, it's usually the size. What volume of the reactor do we need for this particular reaction? If it is a PFR that we're going to use, if it's a CSTR that we're going to use, or if we're just simply going to use a simple batch reactor. But if a particular reaction does not specify a particular reactor to use, then there is a portion also here in reactor design that you are the one who is suggesting what type of reactor is best suited for that particular reaction. That is why you have here the type of the reactor. As to method of operation, so it could either be continuous or by batch. So when we speak of continuous, we have the two ideal reactors, the constantly stirred tank reactors or the back mix reactor, or we have the plug flow reactor, otherwise known also as the tubular reactor. So these are the two ideal continuous reactors. Whereas as we speak of the batch reactor, as the name suggests, batch, so the operation is by batch. It's not continuous. Now, what are the factors that we need to consider in predicting reactor performance? When you speak of reactor performance class, it's the volume that is being processed per unit time. So that could also be reactor performance, or it could be also conversion. What is the degree of conversion of your particular reactant in a particular reactor, let's say batch or CSTR or plug flow. So these two speaks of the performance of your reactor. So there are two factors that are very important, shall I say, governing when we speak of how well your reactor will perform a particular duty that it is to perform. So we have temperature and composition. So for endothermic and exothermic nature of the reaction, of course, temperature has something to do with it. For the rate of heat addition, the rate of heat removal to and from the system, we need also to look into that. And as to the flow pattern of the fluid through the vessel. So the flow pattern of the fluid through the vessel is of course governed by, number one, its volumetric flow rate or its molar feed rate, and of course the nature of the system itself. Okay, but generally these are the factors that we need to look into when we want to look into how well our reactor is going to perform. Now, when we speak of design of reactors, the actual design is based on these three ideal reactors. We have the batch reactor, we have the CSTR, and we have the tubular reactor. Okay, so these two are continuous, whereas we have the batch here. Now we have also industrial reactors, which we can have also the simple batch reactor as one. We can also have an industrial reactor, which is the CSTR. And we have also the industrial reactors, which could either be having beads inside. So we can have the fixed or packed bed reactors. These are tubular in nature. And we can also have the fluidized bed reactor, wherein your system is flowing through a packed bed. So it's said to be fluidized reactor also. So these are industrial reactors, and as my experience would tell me, oftentimes we don't reach this part. But we'll see if in your case we can reach this one. Okay, so depending on how many cancellation of classes we have and how well is your reception to the topics before this. But it's a must that we will cover these three: the batch, the CSTR, and the PFR. Now, if we talk about homogeneous reactions, they are actually carried out in batch reactors. They can also be carried out in steady state flow reactors. This means it could also be carried out in CSTRs or PFRs. They can also be actually facilitated in semi-batch fashion, or this is what we call the unsteady state flow method of operation. But in here, in our kinetics, since this is fundamental in nature, we don't tackle topics that are semi-batch in nature. So we only have the batch and the continuous type reactors. Now, as illustrated in our journal reference book by Octave Levenspiel, so you have here figure 4.1, classifying the reactor type. So in letter A, you have the batch reactor. So this is how it's illustrated there. Letter B, you have the steady state flow reactor. This one is actually your plug flow reactor, tubular. So we envision that our reactant is being converted as it flows through this tube and eventually leave as converted reactant already on this side of your tube. Then for CDE, we have the this one. You have, in the case of C, you have volume and composition at any particular time is changing. So the volume and the composition inside the reactor is changing. Now in here, you have volume changes, but composition is unchanged for letter D. And for letter E, you have volume is constant, but composition is changing. Now, the C, D, and E, which I have mentioned a while ago, will not cover, are actually constituting the semi-batch operation or the unsteady state method of operation. We will only be covering the batch and the continuous. So that would be the PFRs and the CSTR. Now, the CSTR, these three ideal reactors are seen here. So you have here the batch, you have here the plug flow or the tubular reactor, and you have here the CSTR, also known by the way as mixed flow reactor, also as back mix reactor. Back, B-A-C-K, mix, M-I-X in one word. So back mix reactor. Okay, so you have these three ideal reactors to base on your design of single reactors or multiple reactors. So when you speak of multiple reactors, it can either be made of one type or they can be a combination of several types. Okay, now we look into the simplest of the three. It's the simplest because it's batch reactor. However, the performance equation for this is not as simple as the second type under the continuous flow reactor. Okay, you will learn later when I'll show to you already the performance equation. Now, I will try to have this particular slide here next to the batch reactor slideshow. Just interrupt if it will not show, because this one is not from YouTube. This is not a YouTube video. This is coming from chemical engineering software for video depicting the operation of a batch reactor. So hopefully it will show there in your end. If not, then I will just share the original slide, not in PDF form, in your Canvas. That way you can review it again. Okay, so let's see.
Batch reactors are the simplest reactors used in the chemical industry. The reactants are placed into the reactor and then allowed to react, and products form inside the reactor. The products and unreacted reactants are then removed and the process is repeated. Batch reactors contain ports for injecting reactants and removing products, and can be outfitted with a heat exchanger or a stirring system. These are generally of constant volume. Some are designed to maintain a constant pressure by varying the reactor volume.
Okay, so I hope you got the last part. So so it's not shown. You can only hear it, no video. Okay, so I'll just share this with you. I'll just share this with you as, as a PowerPoint slide with the videos. That way you can look it up again at home. Now, in the case of the batch reactor class, the reactants are placed into the equipment, the batch reactor that is. Then they are allowed to react. They are made homogeneous in the entire time that they are allowed to react. Then after a considerable time, wherein a portion or if not all of the reactants have been converted to the product, they are withdrawn from the reactor. That's just how simple it is. It's as if you're cooking something, and after it's done, after it's cooked, you take it out of the pot. So it's the same with the batch reactor. So if you were listening to the audio, it says there that it can be operated at constant temperature, but it can also be operated at constant temperature, constant pressure. That's in the case of varying the volume inside the reactor. So that's what you have covered. That's what we have covered rather in module 3. So if it's just constant temperature, constant volume, so that's the usual case, but it can also be constant temperature, constant pressure, wherein the volume of the system itself inside the reactor is being varied. That's in the case of the batch reactor. Now, what are the things that we need to know about the batch reactor in terms of its key characteristics? So the operation here is unsteady state. It changes with time, the operation that is. So there is no spatial variation of concentration or temperature. So as I have mentioned, at any point inside your batch reactor, your system is having the same concentration. It's well mixed and the same temperature. However, it has as a very given, shall I say, limitation for the batch reactor is that it's only used for small scale operation and suitable for slow reactions, mainly but not exclusively used for liquid phase reaction. So mainly used for systems that are liquid in nature, but it's not exclusive only for this type of system. So it can also have the solid liquid system or even the gas system. But as it says here, not exclusively for liquid reactions only. Now, in here, we have to consider the charge in. So you charge, you put in your reactants, and then the cleanup times. So you place everything, you let them react, then you take it out, then you clean it, then you put another system that you want to have reacted inside your reactor. So in here, we have to consider these two, the charge in and the cleanup times. However, due to its simple design, sometimes it's preferred by small-scale operations only. So since we did not have really very intricate, shall I say, auxiliary equipments attached to it, okay, compared to the continuous flow reactors. Okay, so needs little supporting equipment, but it can be jacketed as well. Pwede siya jacketed in case of reactions that need to have cooling or heating in the process. Okay, so that's for the batch reactor. This is how Levenspiel wrote the or illustrated the batch reactor. So you have symbols like pi o and pi. So I will explain what's this pi o and pi that you see here in the symbol. So by the way, these are batch reactors that you see here, left and right. So this is your batch reactor at time 0, and this is your batch reactor at time t, meaning a certain time has already elapsed. Now, constant pressure, this is constant pressure, so meaning this is varying volume. This is constant volume in here. Okay? Now, your pi o, so your pi o is your total pressure of the system initially. So 0, 0, pi sub 0. B sub o is the initial volume. And N sub AO is the initial number of moles. The small p sub AO is the partial pressure of A initially. And since this is at time 0, for this batch reactors here, it could be like this or this. Your CAO, XAO, or that's the amount of A converted, is equal to 0 because this is the start of your reaction. Okay? For after some time, so varying volume, you have it here, constant pressure. So you have pi as the final total pressure of the system. V is the total volume of your system. N sub A is the total number of moles. Rather, it's the number of moles only of A after some time. And small p sub A is the partial pressure of A after some time. So in here, we have already a certain amount of A that has been converted. So you have here CAO. This should be CAOXA, not anymore equal to 0. Because of course, A had been one way or the other partly converted, if not fully converted. Okay, so these are the representations that you will encounter for the batch reactor, whether constant volume or varying volume. Now we go to the steady state flow reactors. Do you have any questions? Okay, so if there's none, I will continue. So for steady state flow reactors, we have the mixed flow reactor or the CSTR or the back mix reactor. So these are used in industrial processes where large quantities of materials are to be processed at any particular time. So this is used when rate of reaction is fairly high or extremely high. So in contrast with the batch reactor a while ago, it's only for low rates of reactions, low speed that is. Now supporting equipment here is might be great in some instances. And however, though in terms of design, there's a lot to consider when we talk about these continuously steered tank reactors or your PFRs. We have extremely good product quality control here. So meaning there is much control, or you can control the amount of product that is being produced. So actually, between the CSTR and the PFR, you will know as we go along which of the two even gives a much higher percentage yield of the product. So you have to take note of this as the advantage over the capital expenditure, since we have supporting equipments most of the time for these two, the PFRs and the CSTR. So you have extremely good quality control of the product. And this one is widely used in the oil industry. Now, we move on. So for the tubular reactor, otherwise known as the plug flow reactor, these are the key characteristics. Okay? So steady state operation, spatial variation in axial direction but not in radial direction. Axial meaning along the axis of your tube or of your pipe representing your plug flow reactor. Now we see a change in the concentration because there is conversion of your reactant as it progresses along the tubular reactor or along the path, okay, of the tube. There is no, however, radial direction, shall I say, variation. There's no variation in the concentration in terms of uh, the radius. So let me just explain what this two means. So if you have a plug flow reactor, just have it illustrated here. And let's say this is the axis of your reactor. The one that is referred in here that there is special variation in axial direction. So meaning concentration in here, Ca1, of course, is different from the concentration in Ca2. Okay, that's axial, in axial direction along the axis. Primarily, as explained, there is already conversion of your reactant as your reaction proceeds or progresses along the tube. Let's say this is your inlet and this is your outlet. Now, however, there is no radial direction. So if I will have this erased here, and I'll draw here. So this is a tube, so this must be a circle. And this is radius. This is the radius of the circle. Okay. Coinciding with the axis that we have in here. Along the radial path class, there's no variation in concentration in here. Anywhere from the center going out, as long as we're talking about the same radius, there won't be any changes in the concentration of A. Or let's say if A is our reactant. So no variation in radial direction. However, axial, there is. Okay? So keep that in mind. The difference between axial variation in concentration and radial variation in concentration when there is that for your tubular reactor. Now, this is suitable for fast reactions, mainly used for gas phase reaction. Take note of this. Okay, I did not mention it a while ago because anyway, we're going to progress in this slide. So for gas phase reaction, this is preferred. This tubular reactor is preferred over the mixed flow reactor. Now, your control for temperature here is difficult. However, even though it's difficult to control the temperature here, since it's tubular in form, there is no moving parts. And there is no moving parts that will translate to maintenance cost. So low maintenance cost in the case of tubular reactors because there are no moving parts inside to ensure that your system is well mixed. Unlike the batch and the CSTR, wherein you have to make sure that at any particular time, at any point inside your equipment or your reactor, the concentration must be equal or the same. So in this case, there's none. So no moving parts. So in terms of maintenance cost, this one is having lower maintenance cost. Okay. Now I will skip this part in here. You can just view it later when you have it already downloaded and referring to the PowerPoint. Anyway, you can see it in here. Now we go further to plug flow reactor. So here, fluid flows through the reactor in an orderly manner without mixing or diffusion along the flow path. So there's no mixing, there's no diffusion of fluid elements along the flow path. It's as if they're just falling in line, comparable to students falling in line during flag ceremony, and they also fall in line and go back to their classrooms after. So there is no overtaking. So there is no mixing. Okay. Now residence time of all fluid elements inside the reactor is the same. So the amount of time that each fluid element stays inside the reactor is the same for your plug flow reactor. Now we go to the second type of the continuous reactor, and that is the continuously stirred tank reactor, now also known as the back mix reactor or the mixed flow reactor. So these are the key characteristics of the CSTR. So it has also steady state operation. It operates steady state, do not change with time. It can be used in series. Actually, PFRs can also be used in series, and this can be combined as well with PFRs in series parallel combination. Now, no special variation of concentration. So at any point inside your reactor, there's no variation in concentration, even temperature. So it's well mixed. Mainly used for liquid phase reaction and suitable for viscous liquids. So in terms of special application, so it's suitable for viscous liquids, referring to the continuous stirred tank reactor, the continuously stirred tank reactor. Now we have the semi-batch, though we will not be covering it in here. You can look at the way it operates, and you can closely compare it with the batch and the CSTR. Okay, once it's already shared to you in Canvas. Now, what about semi-batch? So this offers good control of reaction speed. A while ago, I emphasized that when we talk about continuously stirred tank reactors or continuous reactors, we say that there is extremely good product quality control. So we have control on the yield, we have control on the amount of product that is produced from our system, from our reactor. Now, if it's compared to the semi-batch, what is good about the semi-batch? This is it. So it offers good control of reaction speed. So this time, you can control the speed of the reactor, or the reaction rather. The speed of the reaction can be controlled in the case of the semi-batch reactor. Now, this is mainly used in colorimetric titration in the laboratory. So a small reactor in the laboratory that is operated in semi-batch fashion. For steel production, in the case of industrial application, you use the semi-batch reactor. So it's a combination from the term semi-batch. It can be batch, it can be continuous. So shall I say, an intermediate between the two, the batch and the continuous. So we have the semi-batch. Okay? Now, before we go to the performance equations for our ideal reactors, we of course have to perform the general mass balance. So we need to know what we need to balance. So actually, when we balance something in anything, in any system, there is this particular component that we use as a basis. So that particular component entering your system must be the same amount of component that leaves your system in whatever form it may leave the system. So when we speak of design of reactors, now the rate of reactant flow into the element of volume, so this is your element of volume, a cube. Now the rate in which the reactant enters this cube should be equal to the rate of the reactant flow out of the element of volume plus the rate of reactant loss due to chemical reaction within the volume. So notice, class, that you don't only say that the amount that goes in should be equal to the amount that goes out. There is already an amount that has been converted, and that is the amount that is accounted for in here in the second term on the right. The rate of reactant loss due to chemical reaction. So you cannot account it in here and on the reactant that leaves your system because it was already converted. So that needs to be accounted for. And next is the rate of accumulation of the reactant in element of volume. Is there an accumulated amount of reactant that remains at any particular time in your element of volume here? If there is, then this has to be accounted also. But later on, you will know when we speak of the batch and the continuous reactors, we have two, the CSTR and the PFRs, that there are terms here that we can equate to zero. because they don't apply for that particular system that we are applying the mass balance on. Okay, so but this is our shall we say general or generic mass balance equation. Input is equal to output plus amount lost due to chemical reaction plus the rate of accumulation, if there is any amount accumulated within this element of volume. Okay? Now, if we do mass balance in our reactor or in our element of volume for our system, we also do energy balance on it. So general heat balance equation is the same thing, exactly the same thing as the mass balance equation. In here, you have energy coming in, so heat that flows into your elemental volume or fluid is equal to the rate of heat flowing out of the element of volume plus rate of heat disappearance by reaction. So by reaction, maybe the reaction already consumed a certain amount of heat for it to be able to proceed or happen at all. So that needs to be accounted for. And the rate of accumulated heat, if there is this accumulation of heat within this element of volume. Okay, element of volume of your system. So your mass balance and your energy balance are all actually the same in terms of form. They only differ in what you are balancing. Okay? Now, so when we go to our batch system now, so we're going to look into each of our systems and write down our performance equation for that particular system. So this is our batch system. If I will ask you for the batch system, if you have that mass balance equation below, input is equal to output plus accumulation plus rate of disappearance, what term or terms here do we equate to zero? Or what term or terms here are zero since we have the batch system? Everybody, we have the batch reactor here. You place in the reacting substances inside. Then after some time that they have reacted, you take it out, you clean the reactor, and then place a different system inside again. So that's just the way it goes with batch systems. Now, if this is your mass balance equation for a batch system, what do you think is, or what do you think are zero in the terms that you see? Accumulation. Accumulation. What about the others? Let me see. What do you think is zero or are zero? I have two answers or three answers already. 1, 2, 3. Accumulation, accumulation, accumulation. This is the case wherein they say input, output. This is the case when they say class that the majority often is not more, is not at all times correct. Or okay, you can apply it in anything. I don't want to make you speculate on anything that is on my mind, but never did in the history of anything that the rule of the majority always works. Okay. In this case, I only have one exception. In the case of the batch system class, the terms that you can set here to zero are the input and the output. Okay, we don't have input and we don't have output because this is not a continuous system. We don't put in continuously anything into your reactor. We don't put any. We don't take out anything from the reactor itself. So we don't have input and output for a batch system. What we have is the accumulation and the rate of disappearance. So that's the remaining terms. These are the remaining terms for your batch system. Okay, so I will Here, my markings here. Now, if we will take out the input and the output, then I'll proceed to the next slide. The rate of reaction is equal then to the accumulation. This rate of the reaction or the rate of disappearance is equal to the accumulation. So if we do that, this would be the left side, and this would be the accumulated. The rate of change of the number of moles at any time in your tank or in your reactor. Now, if you will transfer, we'll just increase the size of this. If you will transfer the V here, you'll transfer it here, you will have now dCA dt. We know that C is equal to N, C sub A is equal to NA over V. So you have now this one. Now we can also write this NA here, DNA. So remember this D can be written as, write this as NaO 1 minus XA. Just like CaO times the quantity 1 minus XA. So the same form, we only change Ca to Na. So in this case, we have NaO. Now, if you do the differentiation of this expression that we have here, it would be something like this, right? Because the D of NaO is a constant. So that would be derivative of a constant 0. So you'll get the derivative then of XA, which is dXA. It's negative, and this one is negative. That makes it positive in here. The V is still written below. So from this one, you'll have this. Okay? These are equations actually that you could see as well in Devon's field and how they are converted from one form into another. But the starting point is this one. Okay? This is your rate of reaction, and this is the rate of accumulation. The way the number of moles of A changes in your reactor at any particular time. Now, this NaO over V, just like this one. So if this is NaO over V, then it would be CaO. So from this one, you have now this. Okay? Just like from in here, you have this. However, our performance equation will actually be the last one. I'm just showing to you the different forms of the equation, performance equation for a batch reactor, and the main equation that I would suggest you memorize or you really take note of. Now in here, you can interchange the things that you see in here. The dt you can place in here. The rate, which is dependent on the reaction itself, whether it's first order, second order, and third order. So it will be a general expression, depends on the rate law. So you place it here together with the V, and then NaO set aside. So what you did actually is just switch the dt and the Ra in here. NaO was placed before the integral because it's a constant. So from that one, you will have this. And since this NaO and this V, if it's a constant volume system, can be grouped together into one expression, CaO, then this is your final equation. For your batch reactor class, for your batch reactor, this is your performance equation. So they will all differ. The performance equation for a batch reactor will only differ where? It will only differ in here, in the rate expression. So depending on what is the rate law. So you just plug in the appropriate rate law as was taught to you on how to determine from chapter 3 of your book. So you plug it in here and then you process this expression already. Since the rate law is in terms of concentration, then there's a need for you to convert the concentration into conversion because we have here conversion. Okay, but you can also have it in terms of concentration if you want to. Now, this one is your performance equation for the batch reactor in terms of conversion. Okay, in terms of conversion. Now, I will ask a question. What if you need to write down a performance equation for a batch system in concentration form? This one is in conversion. I want it written in concentration form. How would you write it? How would you write the performance equation in concentration form? Anybody? You can write it in the inbox or you can use your earphones, headphones. How will you write the performance equation for a batch system in terms of concentration? Because this one is in conversion. Para bala nga ginapamangkot na kamo ni kay para bala hindi na kamo mag-ilis-ilis diyo sa rate law nyo abi karon concentration na di siya di kinahanglan nyo pa na siya i-express in terms of conversion if this is your performance equation. Now, how would you write the performance equation for a batch reactor in terms of concentration, not conversion? What will you do? Nothing happens here on the left. We keep what is written on the left side, that is the integral of dt from 0 to t. Actually, this left side is the t already. The residence time, okay, or the holding time for your batch reactor. What will be the changes that you'll see on the right side? We're done with this in the third module. How will you write the performance equation in terms of conversion? Sorry, in terms of concentration. Wala gid sang may matay. Done na tani. Third module, we're finished with this. How will you write it? I'll erase the markings here so I can write. I'll erase this one. So this is your performance equation in terms of conversion. What's the performance equation in terms of concentration? Oh, I get. The left side would still be the same, so it's dt. What do you think will you have here? So since, salamat, there, TCA dt, TCA. Very good. Dami lang ko kapasalamat kay Jericho. So you have TCA rate from CA. Try to change this to CAO quantity 1 minus XA. Isn't it like this? We have done that in module 3. Your CA is CAO times the quantity 1 minus XA. So if you're going to differentiate it, it would be this one. Okay? Nari siya, oh. Nari siya, oh. In-switch nyo lang. I place it here. You just switch the dt here and then the rate here. So this is another performance equation for your batch reactor if you need a performance equation in terms of concentration. Why am I asking you this? As I've said a while ago, so that you will not anymore convert the concentrations that you have in here in terms of A or in terms of B, expressed in terms of A to XA, because in here it's in conversion, so you need to express it in terms of conversion. So this one will directly let you solve for the residence time or the holding time processing the information changes in terms of concentration. Okay? Now, any question? We will continue tomorrow on the continuous reactors.